Thank you. Thank you very much for the invitation. Very happy to be in Stony. Brook. I was telling Misha before that so much of the mathematics I do, one way or another, originated from this place. So I prepared a very, very accessible talk, but hopefully I'll be able to say something interesting also for the experts. So it's a talk about symplectic geometry. I mainly work in symplectic dynamics, but I'm already speaking the dynamics seminar, so this talk will have very, very little dynamics, almost none. There will be Hamiltonian flows, though. So let me quickly overview the setting. So I'll be considering the simplest symplectic manifold possible, namely the symplectic vector space, R2n, equipped with a symplectic form, dx dy. So xy, xn, y1, yn are this is a typo, it's dxi, which dyi, sorry. So xi, yi are the coordinates on R2n. And I'll be considering Hamiltonian flows on R2n, and more precisely flows of autonomous Hamiltonians. So it's known that autonomous Hamiltonian flows preserve energy, and so the flows preserve the level sets of any Hamiltonian. So more precisely, your Hamiltonian function h on the symplectic vector space defines a vector field by this equation, which is Hamilton equation. Omega of the vector field is equal to dh. You can integrate the vector field, and let's say you can integrate the vector field if the Hamiltonian grows, for instance, towards infinity. You have a global flow, and the flow preserves all the energy, all the level sets of your Hamiltonian. Now, a nice feature of Hamiltonian dynamics is that actually the qualitative Hamiltonian dynamics is completely defined by the energy hypersurface, by the level set of the Hamiltonian. You don't need the Hamiltonian function to speak about the flow up to reparametrization. Indeed, if you restrict your symplectic form to the energy hypersurface, assuming that, say, C here was a regular value of your Hamiltonian, so sigma is a smooth hypersurface. If you restrict your symplectic form to sigma, you don't have a symplectic form anymore because sigma is odd-dimensional. So the restriction will have a one-dimensional kernel, and your Hamiltonian vector field is just a nowhere vanishing vector field that takes value into this kernel. So you see that up to rescaling, this vector field is completely determined by the hypersurface sigma. And now in symplectic dynamics and also in symplectic geometry more generally, people study periodic orbits of Hamiltonian systems for dynamical reasons, but also because their periodic orbits govern, in some sense, certain rigidity phenomena in symplectic geometry. So a periodic orbit is just the orbit of a point that closes up this way, closes up after some time. So associated to any periodic orbit, you can associate an action. There are several notions of actions in symplectic geometry, but for autonomous Hamiltonian system, the notion of action that I'm going to use today is sometimes it's called the symplectic action. It's the simplest possible one. It's just given by this expression. You integrate the symplectic form over a disk that kept your periodic orbit. And this two form here is actually exact. So if you fix any primitive, this integral is just the integral of the primitive along the periodic orbit. So very, very simple. This will be the symplectic setting. And now it turns out that hypersurfaces of symplectic manifold sometimes and often in Hamiltonian dynamics admit a contact structure. They're contact manifolds. So let me quickly review the contact setting. Again, this is very basic. So I only consider R2n as a symplectic manifold in this talk, but I will be considering contact manifolds of any kind, and, well, more or less. So a contact manifold is an odd-dimensional manifold, for me always closed, sigma. I call it sigma because I want the hypersurface of the previous slide to be a contact manifold. So it's an odd-dimensional manifold, closed, in my case, equipped with a contact one form, which is a one form satisfying this condition called the contact condition. Alpha wedge the alpha to the maximum exterior power is nowhere vanishing. It's volume form. I wrote positive, but I meant a volume form. Now, before I said that if you have a hypersurface of a symplectic manifold, that defines a Hamiltonian flow up to reparametrization of the orbits. And here, a manifestation of that is that a contact manifold defines in a unique way a special vector field called the Reeb vector field by these two equations. So let's comment on these two equations. So this contact condition implies that the differential of alpha has a one-dimensional kernel. So the first equation tells you that the Reeb vector field must lie in the kernel of the alpha. So that defines the Reeb vector field up to rescaling, and then the second condition fixes the rescaling. And again, in contact dynamics and contact geometry, people study periodic orbits of Reeb vector fields. There's a famous Weinstein conjecture, which is still open in high dimension at least 5. It says that these Reeb vector fields always admit periodic orbits. And associated to a periodic Reeb orbit, namely periodic orbit of the Reeb vector field, you have an action. That is the analogous notion that in the symplectic setting. So the action of a periodic orbit gamma is just the integral of alpha over gamma, but since alpha of the Reeb vector field is 1, the action here is nothing but the period. So if you run along the periodic orbit, you close up after time tau, that's the action. It's more appropriate to talk about action because sometimes you consider multiple cover of the periodic orbit, which still has the same minimal period, but they have a multiple of the minimal period as action. Now, the contact manifolds I will mainly focus, but I will consider more general contact manifolds in dimension 3, but for most of the talk I will consider contact manifolds that are star-shaped hypersurfaces of the symplectic vector space. So star-shaped for me means, so it's a hypersurface that encloses a compact set, which is a ball. The enclosing compact set contains the origin, and if you draw a line through the origin, it intersects the compact set on a segment. Now it turns out that, and I want more than that. I want all these radial lines through the origin to cut the hypersurface transversely. Okay? So it's more than just the topological star-shapedness. Now, it turns out that any star-shaped hypersurface admits a canonical contact form, which is the one that I drew here, that I wrote here. So again, you consider the standard coordinates of R2n, which you call x1, xn, y1, yn, and x dy minus y dx, say 1/2 for aesthetic reasons, is a contact form when you restrict it to sigma, if sigma is star-shaped. So this is a very important class of contact manifolds. Here's another one, which is one of my favorite, unit tangent bundles of Riemannian manifolds, and for me, closed Riemannian manifolds. So you have your Riemannian manifold, you take the hypersurface of the tangent bundle given by the tangent vectors of norm 1. And this comes equipped with a canonical contact form that you can easily write. I didn't write the expression because I won't need it, but it's canonically defined by the Riemannian metric G. And the associated Reeb flow is nothing but the geodesic flow of your original Riemannian manifold. In other words, here I drew a Riemannian manifold, so it's a deformed sphere. I drew some geodesics on it, for instance this one. This is a sphere of revolution. This is, except that I put it horizontally. This is a meridian. A meridian is a geodesic. Take any geodesic, parameterize it with speed 1. You have a curve gamma of t. And the geodesic flow maps the derivative of gamma, say gamma dot of 0 to gamma dot of t in time t. And the periodic orbits of the geodesic flows project down to the Riemannian manifold to closed geodesics of the Riemannian manifolds, which are important objects in Riemannian geometry and symplectic dynamics as well. Now, arguably one of the starting point of symplectic topology is famous theorem of Gromov, Gromov non-squeezing. It says the following thing. So it says that you cannot squeeze a large ball in a thin cylinder. But you have to be precise in what you mean by squeezing. So the ball, the round ball will be just the round ball in the symplectic vector space of radius r. And the cylinder will be the symplectic cylinder. I will denote it by Z, it's common notation. Cylinder is just the two-dimensional round ball times R2m minus 2. And yeah, and this B2, this is a symplectic splitting. So this B2 is x1, y1. Right, so now if the radius of the ball is smaller than the radius of the cylinder, then the ball is contained in the cylinder, and the inclusion in a trivial way is a symplectic map, in the sense that it preserves the symplectic form trivially. Now what's not trivial is that if the ball is radius larger than the radius of the cylinder, then you cannot find, well, you can always squeeze the ball with a transformation that perhaps preserves the volume and squeezes the ball, makes it very elongated and thin, and puts it inside the cylinder. But if you want to do that with a symplectic transformation, namely with an embedding that preserves the symplectic form, that's not possible. That's the radii prevent that. Now, so Gromov's proof of the non-squeezing is based on, well, he famously introduced holomorphic curves techniques to prove it. And since Gromov's work, there have been different proofs of it that have really different flavor, more inspired from Hamiltonian dynamics, I would say. And one way to see Gromov non-squeezing is the following. So the reason why Gromov non-squeezing works could be stated as follows. So first of all, both the ball and the cylinder are convex domains, right? So ball is compact, the cylinder is not, but they're both convex, convex in the usual sense. You take 2 points in the domain, you draw the segment between them, the segment is contained. Second, I said before that if you have a hypersurface on a symplectic manifold, you have a naturally defined Hamiltonian dynamics on it, defined up to time reparametrization. And you also have a well-defined notion of action for the periodic orbits. And the notion of action doesn't need the Hamiltonian. Again, it's fully defined by the curve, by the geometric curve itself. Now, it turns out that the boundary of the ball, the Hamiltonian dynamics is pretty boring. Is actually all the orbits are closed, and they all have action pi r squared, where r is the radius of your ball. Now the cylinder also has kind of a boring Hamiltonian dynamics on its boundary. It's foliated by the periodic orbits that like the one that I drew here, namely the circle of B2 times a fixed point of R2m minus 2. And all those periodic orbits have action pi capital R squared. So you see you have two convex domains. The first one has a periodic orbit of a certain action, and I stated correctly. Yeah, so the first one has a periodic orbit of a certain action, and the second, sorry, this sentence is not precise. What I meant was that the periodic orbits on the boundary of the cylinders all have action pi capital R squared. In particular, the minimal action is pi capital R squared because all the actions coincide. And what I mean when I say that these are the reasons for Gromov non-squeezing is that if now you replace ball and cylinder by two convex domains that have the property that here you have a periodic orbit of a certain action, and the minimal action of the periodic orbits here is lower than the action of some periodic orbit here, then you cannot squeeze. You cannot send the first domain into the second with the symplectic transformation. Now, this sentence may be disturbing for a symplectic topologist because, well, not this sentence here, this condition here, because convexity, so Gromov non-squeezing is a symplectic phenomenon, but convexity is not a symplectic property. If you take a convex domain in, say, R2 even, you can find a symplectic transformation, which is just an area-preserving transformation that destroys convexity very easily. So it seems, so this fact that convexity is not a symplectic invariant concept is what causes some difficulty in what I'm going to talk about in a moment.
Where do you use convexity in the argument?
Well, I didn't give you the argument, right? I only told you that for now, I'm just asking for an act of faith. If you give me two convex domains and the minimal action on the boundary of the first is less than the minimal action on the boundary of the second, sorry, the opposite. If the minimal action of the orbits in the first domain is larger than the minimal action of the orbits in the second domain, you cannot send the first domain in the second with a symplectic transformation. I didn't give you the argument at all for now.
But you need convexity.
Yes, so if you drop convexity, what I just said is false. It's false. And can I give you an example? Perhaps I give you an example towards the end, because it would take, since I didn't put it on the slides, it would take me a little bit. But it's easy to come up with an example, it's not. Yeah, so. Now, this Gromov no squeezing motivated the introduction of symplectic invariants, which became very popular. They're called symplectic capacities. So symplectic capacity, this is terminology is due to Hofer, I believe. And it's perhaps motivated by geometric measure theory. There are other notions of capacities. So symplectic capacity is an invariant that's available. There are several recipes for them. They're available in high generality, but I will only focus on the symplectic vector space. So a symplectic capacity on a symplectic vector space is a function, C for capacity, defined on the family of subsets of your symplectic vector space, and it's non-negative, and it satisfies these three conditions. First one is monotonicity. If one domain is smaller than another one, meaning that you can embed the first domain in the second with a symplectic embedding, then the capacities are ordered. Capacity of the first domain is less than or equal than the capacity of the second. As would do, say, a measure or the volume. So the volume would satisfy this. Because, I didn't say, but symplectic embeddings preserve the volume form given by the symplectic form to the power n. And stop me if you have questions. So, second condition, capacities are too homogeneous with respect to scalar multiplication of the domains. So capacity of Ru is R squared capacity of U for any non-negative R. So if you only ask for these two conditions, the volume to the power 1 over n would satisfy them. So here's the third condition, which is really the symplectic condition. It says that the capacity of the ball and the capacity of the cylinder of the same radius is pi R squared, which was the minimal action of the periodic orbits on their boundary. The pi is there for, well, for historical reasons, but also because if you put the pi, it's really an action. Now, capacities are hard to construct. And actually, the fact that capacities exist is a consequence of Gromov no squeezing. So, Gromov no squeezing gives you for free, it's a deep theorem, but once you have the theorem, you have for free two capacities. The smallest possible capacity and the largest possible capacity, so that all the other capacities are in between these two. The smallest capacity is defined the following way. You just take the largest capacity of a ball that you can embed symplectically in your domain. Pi R squared, I remind you, is the capacity of the ball. Okay, so you have your domain, you try to squeeze in this is supposed to be like the symplectic image of a ball. Ball can get deformed, but cannot get deformed arbitrarily. Gromov no squeezing tells you that the action of the periodic orbits cannot get too small, cannot get smaller. Yeah, the biggest capacity is the same thing, but with the cylinder. You have your domain, so you define it as the minimal capacity of a cylinder in which you can embed your domain. Okay, so it's infimum of pi R squared, such that you embed symplectically in the cylinder of radius r. Now, here's a third capacity, which is very easy to define, but it's not easy to show that it's actually a capacity. It's the displacement energy. So it's the infimum over all the Hamiltonians H on your symplectic vector space, and you should also allow Hamiltonians that depend on time and consider its Hamiltonian flow from time from 0 to 1. And these Hamiltonians, so you take the infimum over all the Hamiltonians such that the time one map of the Hamiltonian flow displaces your domain away from itself. The image of your domain under the D field has trivial intersection with the domain. And then you measure this quantity, which is the integral of the oscillation of your Hamiltonian for time going from 0 to 1. Time 1 was the time of displacement. There's nothing special in 1. You could have fixed 2 and put 2 here. You would have had another displacement energy with same properties. So it's easy to show that this is monotone, homogeneous, but it's hard to show that it's on a ball and on a cylinder. The displacement energy is what it is. It is what it's supposed to be. It's pi r squared. And then there's another class of capacities, which are easy to show that they are capacities, but are hard to define because the definition is a complicated recipe that requires either some involved nonlinear analysis or holomorphic curve techniques, flow homology, or symplectic homology. So these capacities are usually form a class of capacities which I call dynamical. It's not standard terminology. So they're dynamical capacities because they are actually action selectors. By these I mean that for this class of capacities, which I'm not defining to you, sorry about that, if you apply these capacities, this dynamical capacity, to a domain which has a smooth boundary, which is a contact manifold, then the value of the capacity lies in the spectrum of the boundary, where the spectrum of the boundary is the collection of the action of the periodic orbits in the boundary. For instance, here I'm just working in the symplectic vector space, but if my domain lived in a cotangent bundle and I took as domain U the unit ball tangent bundle, the spectrum of the boundary would just be the set of lengths of the closed geodesics of your underlying Riemannian manifold. So here's where convexity comes in, coming back to the convexity condition. Now it turns out that it's not a consequence of the definition of capacity, but just for all these capacities available on the market, which are dynamical in flavor, if you apply them to a convex body, not only they pick an action value of the boundary, but they pick the minimal one. They pick the so-called systole, the minimal element of the action spectrum, the minimal action of a closed Reeb orbit on the boundary. Now, I'm not going to define capacities because it would be technical. It would take. I'm not going to define these capacities because it would take a while, and I prefer to speak about something else. But just throw in some names, just in case you're curious and you want to check in the literature. First capacities were introduced by École and Hofer, and they carry their name. They're called École and Hofer capacities. There's the Hofer-Zehnder capacities, and then there are more recent capacities. Well, they're all pretty classical. They go back to the 1990s, and their capacities constructed with symplectic homology, and more recently there are capacities constructed with other technology, microlocal theory of sheaves and so forth. You have a question?
Didn't you say that the existence of periodic orbit is conjecture?
Right. So the existence of closed Reeb orbits on general contact manifolds is a conjecture, but for star-shaped hypersurfaces of the Euclidean space, it's a theorem. Right. So for contact type so for domains in R2N which have contact type boundary, it's a theorem. I should have said that. Thanks for asking. Yeah, that's important otherwise. Right. Actually, it's a theorem that these capacities, in a sense, are a way to prove that theorem. The fact that these are.
Sorry, are these systems defined for general symplectic manifolds or just for?
So, but the system considered here is defined for contact manifolds. It's the minimal action of a closed Reeb orbit of a given contact manifold. The du is the boundary of my domain. I'm assuming it's smooth and contact type. You can also talk about the systole of just the smooth boundary of a domain that's not contact, because you have a notion of action, but it's somehow less. Cannot say much about that.
I probably ask about whether it's in Arcturian or just in general symplectic.
Right. No, you can define it in general contact manifolds. Yeah, notably for, the systole of a Riemannian manifold would be the systole of its unique cotangent bundle. And it's sort of a study of it is called systolic geometry. Now, there's a generalization of the notion of capacity. I won't spend much time on it, but I just mention it because it's will come up again later on, very briefly. It also gives you another way to define capacities. So to state the non-squeezing. So consider symplectic ellipsoids. So ellipsoids in the symplectic vector space. So these are the usual ellipsoids. So they're defined by well, they're not usual ellipsoids. So they're defined by n values, a1, an, which you should think of as radii squared, or more precisely, action values. And this is the set of points in, well, I'm writing the symplectic vector space as Cn just for aesthetic reasons. The set of points in the symplectic vector space satisfying the ellipsoid inequality with this radii, with this aj playing the role of radii squared. Instead of putting here 1, I put 1 over pi for aesthetic reasons. So if you do that, so the ellipsoid is a convex domain. So in particular, it's star-shaped. So the boundary of the ellipsoid is a contact manifold with a canonical contact form. So it has a canonical Reeb flow. And the Reeb flow is the simplest Reeb flow you can come up with. Namely, it's the harmonic oscillator. So the Reeb flow in time t applied to the point z1, zn of the ellipsoid rotates the factor zi, where every zi rotates with angular velocity ai. Okay? So angular velocity 1 over ai. For instance, if you take the point where all the zi are 0 except z1, you are in a periodic orbit of period a1. Same for z2, you have a periodic orbit of period z2, in which all the entries are 0 except the z2 entry, and so forth. So you always have at least n periodic orbits of action a1, an. Now the action spectrum of the ellipsoid, for what I just said, is the set of multiples of the ai. And now I generalize the notion of capacity, define the notion of k capacity, where k is an integer, is a positive integer, strictly positive. So a k capacity, it's like a capacity, meaning it's a function of the same kind that satisfies monotonicity and homogeneity exactly like the capacities, but now the normalization that you have doesn't require any more balls and cylinders to have the same capacity. It rather prescribes the value of capacities on ellipsoids. So the capacity of the ellipsoid a1, an is the k smallest element in the set of multiples of the parameters ai. And more precisely, this is not precise what I said, let me put it precise. You take all the multiples of the ai. If different AIs have the same multiple, you repeat the multiple. Okay, so you get a multi-set where certain elements get repeated. You order it. The k capacity of the ellipsoid is the k element in increasing order of this multi-set. Okay, and now the capacities that I defined before are just one capacity for k equal to 1. This is because the ball is just the ellipsoid where all these entries a1, an are equal. And the cylinder is a limit of ellipsoids where a1 is whatever it is, and all the other ai are infinite. Okay? And C1 always picks the minimal among the ai. So this tells you that ball and cylinder have the same one capacity. So one capacities are capacities, and k capacities are symplectic invariants of different nature. Now, let me get to so let's see, I started, still have 30 minutes perhaps? Is that a little bit less than 30 minutes, right? Okay, just have keep track. Right, so now, so far I introduced symplectic capacities. It was a long title, my talk had a long title, so first expression in the title. Now let's move to the second expression, which is Viterbo conjecture. Sometimes it's called Viterbo isoperimetric conjecture, but isoperimetric not in the usual sense, in a symplectic sense. So, Viterbo conjecture is about the capacity of domains with volume 1. And if you don't want to fix volume 1, instead of taking capacities, you take capacity ratios. So you take the, given a symplectic capacity, one capacity. See, the associated capacity ratio, so the capacity is homogeneous of degree 2, volume is homogeneous of degree 2n in a 2n dimensional symplectic vector space. So if you take the quotient of a capacity under the volume to the power 1 over n, you get a function that's zero homogeneous, invariant under rescaling. And I call that the capacity ratio, C hat, associated to C. It's not a standard notation. Oh, yeah?
Are there any restrictions with the sets that you can consider?
Yeah, so in practice, yes. But if, say, even if there were, you can always artificially define the capacity of everything just by limits.
Yeah, I mean, the biggest capacity and the smallest one are clearly well defined for everything, but when you put a volume, I would.
So you think about, say, displacement energy, for instance, that perhaps displacing a fractal set would be, right, so yes, I'm going to avoid, so think of nice domains, after all. There are no, we have fractal sets in dynamics, but in symplectic geometry we like smooth objects. Most of it, not always, but most of the time, piecewise smooth at least. Yeah, so, oh, by the way, the volume is the, so symplectic vector space is the Euclidean space. The volume is the Euclidean volume, but just to get rid of, just for aesthetic reasons, let me take the symplectic volume instead. So the integral of omega to the power n, this is the Euclidean volume times n factorial. So that I get rid of n factorial in all sort of expressions. Now, a few remarks on capacity ratios. First of all, if you take, let's compute the capacity ratio of an ellipsoid. So ellipsoids have a prescribed value of any capacity. So the capacity of the ellipsoid is the minimum among the parameters a1, an. As I said before, capacities are 1 capacities. And the volume of an ellipsoid, you can do the computation, is just the product of the parameters ai, at least if you consider the symplectic volume. So here I have to take the volume to the power 1 over n. Therefore I have minimum divided by product of the ai to the power 1 over n. This is always less than or equal to 1. And indeed it's 1 if and only if all the parameters coincide. Namely, if and only if my ellipsoid is really a round ball. Right, so this is first remark. Now, second remark, which appeared in the paper of Viterbo in the early years 2000s. So this is not the remark. So Viterbo applied the following remark, which is due to John. The John ellipsoid, it was already mentioned in the lecture of yesterday at the Simon Center. So for every convex body in R2n, so by convex body I mean a convex compact set which is the closure of its interior, so it's not. So given any convex body there exists an ellipsoid such that the convex body is contained in the ellipsoid, and 1 over square root of 2n of the ellipsoid is contained in the convex body. This is the so-called John ellipsoid. It was already mentioned, as I said yesterday. And so the very existence of John ellipsoid tells you that for any convex body, so for any capacity, now the capacity of a convex body depends on the capacity you choose. Different capacities potentially may take different values of convex body, although conjecturally they don't, but a priori they could. Now the capacity, the ratio of the convex body is going to be bounded from above by 2n of the capacity ratio of the ellipsoid, just thanks to these inclusions and the monotonicity of both the capacity and the volume. And then the capacity of the ellipsoid, we just said it's at most 1. So we get that any convex body has capacity ratio for any capacity that's at most 2n. And now, for the ellipsoid, we're able to compute the capacities, so you can actually do the small exercise of checking which ellipsoid maximizes the capacity ratio, and it turns out that it's the round ball. And Viterbo conjectured, by this bounded by the fact that the round ball is the ellipsoid with the highest capacity, that actually for every symplectic capacity, the associated capacity ratio is maximized over convex domains at the round ball. namely the capacity ratio of any convex body, is at most 1, and is equal to 1 if and only if the interior of your convex body is symplectomorphic to a round ball. Now, again, convexity is a bit disturbing as a concept for a symplectician because it's not a symplectic invariant. This conjecture failed. It's easy to find a counterexample if you don't require your domain to be convex. Perhaps I will mention later on. So it turns out that Viterbo conjecture, which is widely open, has important implications in convex geometry, not convex symplectic geometry, just plain convex geometry. So let me quickly mention it. I'm not an expert of convex geometry, but yeah, let me quickly say it. So consider a centrally symmetric convex body, C, in the Euclidean space, Rn, not in the symplectic vector space, in a vector space of any dimension, possibly odd dimensional. And I want it to be centrally symmetric, meaning that minus the convex body is equal to the convex body. So your convex body is really, it contains the origin, and it's really the unit ball of a norm, of a Banach norm in R2n. Let's consider the dual convex body, which is just the unit ball of the dual norm. So for example, if your convex body is the round ball, the dual one is the round ball itself. And if your convex body is the L infinity ball, which is the cube, the dual convex body is the L1 unit ball, which is the octahedron. And now, so there's a concept in convex geometry called the Mahler volume of the convex body C, which is nothing but the volume, for me the symplectic volume, of C times its dual body. Okay? So whatever vector space you take, the vector space times itself is a symplectic vector space. It's even dimensional. And so this...
just to clarify, so the dual body just means the set of all linear functionals such that the value is less than 1 on the...
Sorry, say it again?
So the definition of the dual convex body is just the set of all linear functions such that it's less than 1 on a given...
Yes, the polar body, sometimes it's also called, absolutely, yes. Yeah, so you can define it also if you don't have a central symmetry. So the Mahler volume is a nice invariant. It's a linear invariant on your convex body, because if you apply the linear transformation to C star is going to be, C star gets transformed by the inverse of the adjoint, and then the volume of the product doesn't change. Now, in convex geometry, people study the extremizers of this Mahler volume. There's a famous theorem of Blaschke in dimension 3 and in dimension 2. In Saint-Malo in any dimension, it says that the Mahler volume is maximized by the round ball, the Mahler volume of the round ball, and it's conjecture due to Mahler that it's minimized by the Mahler volume of the L infinity unit ball. Now this conjecture is a theorem in dimension 2 and 3, but it's open in higher dimension, and this value you can compute it. It's 4 to the power n if you use my notion of volume, the integral of omega to the n. So I'm getting rid of n factorial. So intuitively, I'm not an expert of the Mahler volume, but intuitively the idea is that the Mahler volume is maximized by the roundest possible convex body, which is the round ball, and it should be minimized by the pointiest one. Yeah. Now it turns out, surprisingly, it's a very nice observation of Augstein, Avila, and Karasev and Ostrover of a few years ago, that Viterbo conjecture, if true, implies the validity of Mahler conjecture. So this is really a theorem. It's potentially an empty theorem because it's perhaps the Viterbo conjecture doesn't hold, but for now it's still a theorem. So here's the proof. The proof is marvelous. And so I won't give you all the details, but I just wave my hands. Now consider a pair of convex bodies in Rn, A and B. And when I say convex body, I really want them to include the origin. I really want them to be centrally symmetric, let's say. So they're really unit balls of a certain norm. Now you can take their product. It's a domain in the symplectic vector space R2n. And you can take its boundary and talk about the Hamiltonian dynamics on the boundary. Now this is a bit, so the boundary is not smooth because you have the singular points corresponding to the boundary of A times boundary of B. But away from those, it's nice and smooth. And there's a way to define Hamiltonian dynamics. Well, you can define Hamiltonian dynamics away from the edges. And you can extend just the Hamiltonian dynamics to the edges as well. Or if you want, you can take this, the boundary of this product and smooth it out a little bit and consider the Hamiltonian dynamic of the smoothened out boundary and pass to the limit. Now, turns out that the Hamiltonian dynamic on the boundary of this product has to do with billiard dynamics. And indeed, by the Hamiltonian flow on this product, describe billiard dynamics in which A is your billiard table, and the convex body B dictates the reflection law. Namely, if B is the round, usual round ball, the Hamiltonian dynamics give you just the usual billiard dynamics on the billiard table A with the usual reflection law, which you preserve the angles. And if you take a general centrally symmetric convex body, you have a billiard dynamics which is more exotic. You have the notion of so-called Minkowski billiards, and which you can describe without talking about Hamiltonian dynamics, just geometrical in terms of angles, where basically the B dictates how you measure angles, so to say. Yeah. Now, if you take a convex body times its dual, and you take its boundary, you do Hamiltonian dynamics, well, you're considering a billiard in your convex body, and the reflection law is dictated by the dual convex body. So that implies, that guarantees that if you take now any trajectory of your billiard in C that goes through the origin, this trajectory bounces forth and back. It's a diameter, and it's a diameter of action 4. So basically, the Hamiltonian dynamics on this product has periodic orbits of minimal action equal to 4. And they correspond to the diameter billiard orbits. I understand that this is too vague. I should have given you perhaps more detail, but if you're intrigued, I can give you more details later on, or the reference of this. It's a very beautiful observation of these authors. If you want, this is a way to define the number 4 symplectically. And now you have, if you have Viterbo, you get on the nose Mahler conjecture. So the capacity, if you take now a dynamical capacity, the dynamical capacity of C times its dual, it's going to pick the minimal action of the periodic orbits in the boundary, which we said is 4. And Viterbo conjecture tells you that the capacity ratio of this is at most 1. So the capacity of this is at most the volume to the power 1 over n. So you get the inequality of Mahler conjecture. So, there are questions on this? I have 10 minutes left, don't I? Much slower than I thought. Too bad, but doesn't matter. I will skip perhaps the very last expression in the title. So Viterbo conjecture is widely open, but there are results that points in the direction that it may be true. In particular, it's known that the balls, so in particular, we have a proof of the so-called local Viterbo conjecture. It says that round balls are local maximizer of any capacity ratio. So I have to be precise. This is a vague statement, so let me make it precise. So you consider the space of convex bodies in a symplectic vector space, and you equip it with a topology. Say that you equip it with the C2 topology. So two convex bodies are closed if their boundary are C2 closed spheres. So So, so this is a theorem that in this form is due to Abbondandolo and Benedetti, but it's the end of a story that started with Alvarez Paiva and Balazshev, and there are many authors in between. Now, I myself contributed to a similar theorem for K capacities. Now, it turns out that the rational ellipsoids in dimension 4, namely the ellipsoids where the two entries are rationals, are local maximizers of a certain K capacity where K is determined by A and B. And now, the round ball, which is the local maximizer of the one capacity ratios, and the ellipsoid, the rational ellipsoids, which are local maximizer of K capacity ratios, have one feature, that the Hamiltonian dynamics on their boundary is a pretty boring dynamics from the point of view of dynamics, because all the orbits are periodic. And so the fact that all the orbits are periodic is what dictates, is what governs these theorems somehow. Now, the proof of these statements are based on systolic inequalities in convex geometry. So perhaps I will have time just to say that, and we'll see if. So I won't tell you any more about the proof of that, but I'll just tell you where it comes from. It comes from analogous theorems in contact geometry, which are interesting per se. So, and I also take the occasion to define an important class of contact manifolds, which is the class that is boring from the point of view of dynamics, but is interesting from the point of view of topology. So I consider a closed contact manifold, and let's restrict to dimension 3 for simplicity, but I could give the definition in all dimensions. The contact form is called Besse when all the Reeb orbits are closed. Now, Besse, if you perhaps you know the name, is the name of a collective of authors, mostly French. It's like Bourbaki, but a bit less prolific perhaps. They wrote beautiful books in Riemannian geometry, one of which is a very famous book. The title is Manifold, all of whose geodesics are closed. Geodesic flows are Reeb flows, so this is the reason why contact manifolds of this kind are called sometimes Besse. It's not the universal terminology, but I like it. I'm based in France, I have to. Now, it turns out that when all the orbits of a Reeb flow are closed, then there's a common period for all the orbits. This is not true for general vector fields. Dennis Sullivan gave a counterexample on the sphere of dimension 5, but the vector field he showed is not a Reeb vector field. For Reeb vector fields, the situation is the following. Say you have a periodic orbit, it starts at the point x, it reaches the same point, which I drew. Should identify this disk with the bottom one. But the nearby orbits may wind around twice before closing up. And this is the general situation that you have. Twice or k times, but a finite number of times. And then, if all the orbits are closed and also happen to have the same minimal period, then the contact form is called Zoll. Zoll was a student of David Hilbert, who found the first example of Zoll Riemannian two spheres. Two spheres, all of whose geodesics are closed, and that are not just the round two sphere. And they're variable curvature. Now, given a closed contact manifold, let's look at its actions, the associated action spectrum, which is the collection of the action of the periodic orbit of the Reeb flow. And let me call rho k the kth element of the action spectrum, treated as a multi-set. Namely, you write down in increasing sequence the elements of the spectrum, which is a collection of action of the periodic orbits. And if, say, there are 3 periodic orbits of action 1, you repeat 1 3 times, and so forth. So rho k is the kth element in this sequence. And you can consider, analogously as what we did before, the associated ratio. So this rho k is one homogeneous in the contact form alpha, and the volume is 2 homogeneous, respect to the contact form alpha. The volume of a contact manifold is the integral of alpha wedge d alpha in dimension 3. So this quotient is now zero homogeneous in the contact form. And let me just enhance the definition I gave before. I said that the contact form is K Besse is if it's Besse, namely all the Reeb orbits are closed, and K is the minimal integer such that rho K is the common period for all the closed Reeb orbits. And now the theorem that I gave before, which are the local version of Viterbo conjecture, confirmation of a local version of Viterbo conjecture, are actually a consequence of this theorem here. This is not a single theorem, it's actually a collection of statements which I put in a single theorem. So the first one is actually independent of before, it's interesting per se. So unlike capacity ratios on convex bodies, the rho k ratios are unbounded on the space of contact forms. So you can find contact forms that have arbitrarily small volume but fixed value rho k. But it turns out that the local maximizers of rho k hat are precisely the K Besse contact forms. And the proof of the theorems I gave before are given by just bridging the gap between symplectic and contact geometry with this theorem. So I think my time is up, but do I have 5 more minutes, or 5 you think? Or it's too much? 5 is okay? If somebody wants to leave before, I won't get offended, promised. So to conclude, let me take the case. So these theorems give a characterization of contact forms, all of whose Reeb orbits are closed. And there are other kind of characterizations that arise from of different kind, and I want to quickly give you that, and then that will be the end of the talk. So I start with a theorem that goes back to Stony, that says that it's a theorem about Riemannian geometry, but secretly it's a theorem about Reeb flows. So on a Riemannian S2, consider the closed geodesics, and actually consider the simple closed geodesics, which has the embedded geodesic circles. Now, if all the embedded geodesic circles happen to have the same lengths, then all geodesics are embedded geodesic circles. You don't have open geodesics. You know, in the round metric, all the geodesics are closed, they are all great circles, and they all have the same length. If you now take another Riemannian S2, like this one that I drew, that has 2 closed geodesics, like this orange and this green, that have different length, then the fact that they have different length forces the existence of geodesics that are not closed. For instance, this one that I drew is going to be asymptotic to this neck. So this was a whole theorem of Stony. There was some technical gaps in the proof, but these days there's a solid proof of this theorem. And it's completely open for higher dimensional spheres. And but surprisingly, in dimension 3, with symplectic techniques, we could give a quite major generalization of this theorem. There's actually a corollary of a theorem for Reeb flows. So let me give you the theorem for Reeb flows. This is still Stony's theorem without the picture. Now consider a closed contact 3 manifold, and consider its periodic Reeb orbits and its action spectrum, which is the collection of action of the closed Reeb orbits. So if you have a Riemannian S2, the associated contact manifold is the unit tangent bundle, and the spectrum, this spectrum will just be the collection of the lengths of the closed geodesics. Okay, so this is more general. And now here's a theorem that I proved a few years ago with my friend then Christopher Gardiner, who is not far from here in Maryland. The theorem says that if the action spectrum has rank 1, let me simplify. For instance, if the action spectrum is contained in the integers, all the periodic orbits that you have integer period, then every orbit is closed. The contact manifold is Besse. And so this theorem was new, even in the Riemannian category, and it actually has first the illustration of the theorem. You can do a sanity check to see that the theorem works on ellipsoid. if you take your contact manifold to be the boundary of an ellipsoid, this theorem, oh, I didn't say, but this theorem is only in dimension 3. Yeah? I wish to have a theorem like this in higher dimension, but we don't have the machinery for that. The machinery we use is based on embedded contact homology, holomorphic curves techniques, which are only available in dimension 3, unfortunately, for now. But, so potentially the theorem could be true in any dimension. I don't know, it's an open problem. Let's do a sanity check on the ellipsoid. If you take an ellipsoid and its boundary, it's a contact manifold, its Reeb flow is the harmonic oscillator, as I already said. Now, if the action spectrum has rank 1, like in the theorem, so the action spectrum is given by the multiples of the AI. So if the AI are all rationally dependent, the action spectrum has rank 1, like in the theorem, and indeed all the orbits are closed because it's the harmonic oscillators, or the rational harmonic oscillator. And it's an if and only if. So let me quickly mention, then I really finished, the following corollary, which is the corollary in the Riemannian case, in case, even if you don't like, say, contact geometry, but you like Riemannian geometry, this was still new. Consider this is a direct corollary of this theorem plus a little bit of literature. So suppose that you have a closed surface with a Riemannian metric, and suppose that all the closed geodesics of this closed surface have integer length. Perhaps different lengths, but integer. Then if the surface is orientable, it must be the two-sphere, and every geodesic is closed. So it's a generalization of Lusternik. And if the surface is not orientable, it's even more rigid. If the surface is not orientable, it must be RP2. And it's still true that all geodesics are closed, and in that case, it was known that there's only one RP2 with that property, the standard one, the one with constant curvature. Yeah, and I don't know if this is true in higher dimension. I don't even know what to conjecture. Okay, that was all. Sorry for going a little bit over time.
Thank you.
Questions? Yeah.
So you mentioned billiards at some point. How is what you presented today related with them, and how it can be used to prove some new results in billiard?
In billiard dynamics, yes. So yeah, so I'm not an expert of billiards, but there are a few theorems that one can prove. So that has been proved on billiards. So let's say, so there are theorems about billiards that can be proved with symplectic techniques, and with more specifically about the Viterbo conjecture. I think the Viterbo conjecture, we need to write it down, but the Viterbo conjecture would imply isosystolic inequalities for billiards. So you have a billiard table, and even a usual billiard table with the usual Euclidean bouncing rule, and you want to bound the minimal length of a periodic billiard trajectory in terms of, say, the area of the table. I think, to my knowledge, optimal ratio between minimal length and area of the table is not known, but the Viterbo conjecture will give you a bound that is better than what's currently known, I think. So that would be one. There are other symplectic techniques, but they're a bit unrelated to what I talked about. I myself have a result with Peter Albers quite a few years ago. They give another kind of systolic bound for billiards. It works for billiards that are not necessarily convex. First of all, it implies that any billiard, including non-convex ones, has a periodic billiard trajectory with number of bounces. If I remember well, if the billiard has dimension n, it works also in high dimension, you always have a periodic orbit that bounces n+1 times. It's something that you get out of a Maslov index. And then we can also, if I remember well, we can also bound the length of this periodic orbit in terms of not the area, but the diameter of the billiard table. This comes out. It's because of the displacement energy. So these are theorems. I'm sure that experts of billiards, I'm not sure that experts of billiards, I'm not sure what they think about these theorems. But the systolic inequality, I would say, it's interesting. It's something that it's been looked at in the literature.
Any other questions?
Are there some simple example of Riemannian sphere that is not a standard sphere but has all geodesics?
Oh, yeah, yeah. So, yeah, you can actually, so, Zoll actually gave very concrete constructions, so I cannot give you an example in terms of, say, equations, but I can tell you how the recipe goes. Don't remember it on top of my head, but so it's easy to construct spheres of revolution, all of whose geodesics are closed. And you actually have a lot of freedom for doing that. You take your sphere of revolution is completely determined by the profile function. So you can prove, if I remember well, that a sphere of revolution, all of whose geodesics are closed, has a single equator, a single belly, so to say. Now, if you start from your North Pole, you draw the profile. So you start with an horizontal tangency, you draw the profile. Draw any profile you like until you get vertical. So if you go round, you get the round metric, but draw anyone you like until you get vertical. And then Zoll gives you an ODE to solve to complete this curve all the way to the South Pole. It would look something like this if you take this curve, I think. And the resulting surface of revolution will have all geodesics closed. It's a beautiful construction. It's elementary. It goes back to a century ago, due to Zoll. There are more exotic. So Guillemin proved that there are plenty of Zoll two spheres that are not. So there's no rigidity when there's a yeah. Yeah.
Zoll three sphere, of course.
Yeah, you can do the same. You can do the same. Yes, I don't think it's special dimension 2. It's just in the Besse book they do it in dimension 2, but just for aesthetic reasons. I don't think there's anything special about that. Yeah.
Any other questions? Okay, well, that's thank you.